Every detail in this story comes from real scientific research and observation. Somewhere in our galaxy, a dead star is spinning, not slowly, not gently, but hundreds of times every second, sweeping a beam of radio waves across the cosmos like a lighthouse no one built. It has been doing this for tens of thousands of years. Tonight, you are going there. Welcome to Quiet Science at Bedtime. This channel is still new, and if this kind of science helps you sleep, it would mean a lot if you subscribed, hit like, and turned on notifications. It really does help. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. There are roughly 2,000 neutron stars that we have identified within our galaxy. 2,000 out of an estimated 100 million that are believed to exist in the Milky Way alone. Most of them are invisible to ordinary telescopes. They emit no visible light. They are small. Most measure between 20 and 25 kilometers in diameter, which on a cosmic scale is nearly nothing. A neutron star is narrower than the length of a major city, and yet it contains more mass than the entire sun. 1 teaspoon of neutron star material, if you could somehow lift it, would weigh approximately 4 billion tons. These are not metaphors, these are measurements. Tonight, you are going to one of them, not to study it from a distance, to be near it, to let the scale of it settle into you slowly, the way the cold of deep space settles into everything it touches, not all at once, but gradually, until there is nothing left that is not changed by it. Before we arrive, let us understand what made this place. Every atom in your body was forged inside a star. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was created through nuclear fusion, deep inside stellar cores that burned for millions or billions of years before dying. When a star much larger than our sun reaches the end of its life, something extraordinary happens. The fusion process that has been generating outward pressure, holding the star up against the inward pull of its own gravity, begins to fail. The core, which has been fusing progressively heavier elements, reaches a point where it can go no further. Iron accumulates. And iron, unlike lighter elements, does not release energy when it fuses, it absorbs it. The core stops generating pressure. In a fraction of a second, in less time than it takes you to blink, the core collapses. A region that was once the size of the Earth shrinks to something the size of a city. The outer layers of the star, which have been falling inward, hit the newly collapsed core and rebound in a shockwave of almost incomprehensible violence. The result is a supernova, an explosion so bright that for days or weeks it can outshine the entire galaxy containing it. Billions of stars, and one dying one drowns all of them out. What remains at the center, if the original star was between roughly 8 and 20 solar masses, is a neutron star. You are going to one of those centers now. Imagine the supernova has already happened. Thousands of years have passed. The debris cloud, what astronomers call a supernova remnant, has expanded outward in all directions, cooling and thinning as it goes. At the heart of that expanding cloud, something small and very dense is left behind. You approach it slowly. The cloud around it glows faintly in X-ray and visible light, gases ionized by the energy of the original explosion, still radiating their heat into the surrounding space. There is no sound. There is no air. There is nothing here but radiation, magnetic fields, and the faint pressure of a stellar wind flowing outward from the object at the center. As you come closer, the object resolves. It does not look like a star in the way you might imagine. There is no warm light, no corona of golden plasma. The surface of a neutron star, if you could call it a surface, is a crystalline lattice of neutrons and electrons, packed to a density that ordinary matter cannot approach. The outer crust, which is perhaps 1 kilometer thick, is composed of atomic nuclei arranged in a rigid structure, threaded through by a sea of free electrons. Below that crust, the density increases further. Protons and electrons have been crushed together into neutrons, creating a fluid interior of almost pure neutron matter. Deeper still, toward the core, the physics becomes genuinely uncertain. At those densities that exceed even the nucleus of an atom, we do not yet have equations we fully trust. Some models suggest the core contains quark matter, the fundamental building blocks of protons and neutrons, in a strange deconfined state. Others propose more exotic phases of matter that have no names in everyday language. We do not know. The center of a neutron star is one of the few places in the universe where our best physics reaches the edge of what it can describe. You are floating just beyond the surface now. It is not glowing visibly, but it is radiating. The surface temperature of a young neutron star can reach 1 million degrees Kelvin, hotter than the surface of the sun by a factor of roughly 200. That heat is not coming from fusion. There is no fusion happening here anymore. This heat is the stored energy of the original collapse, bleeding off slowly into space through thermal radiation. The star is cooling, but it will take millions of years to cool to stellar temperatures, and hundreds of millions more before it approaches anything cold. You are next to the remains of something that once burned for millions of years, and it is still radiating the memory of that death. The gravity here is different from anything you have experienced tonight. At the surface of a neutron star, the gravitational field is approximately 200 billion times stronger than what you feel standing on the surface of the Earth. An object dropped from 1 meter above the surface would impact it at approximately 2 million meters per second, roughly 1% of the speed of light, in a fraction of a millisecond. The surface is, in every meaningful sense, inescapable without enormous energy. The escape velocity from a neutron star is approximately 100,000 kilometers per second, 1/3 the speed of light. To leave this place, you would need to be moving at a velocity that even light struggles to achieve. You are not trying to leave, you are simply here, watching. The star is rotating. All stars rotate, but when a massive stellar core collapses from something the size of the Earth down to something the size of a city, the conservation of angular momentum, the same physical principle that causes a spinning ice skater to accelerate when they pull their arms inward, causes the rotation rate to increase enormously. A star that rotated once every several days can, upon collapse, become an object that rotates hundreds of times per second. The neutron star you are near is rotating 23 times per second. You can feel it, not as vibration because there is no medium here to carry it, but as a cycling of the magnetic field around you. The field sweeps past, regular and exact like the tick of a clock built at the end of the universe. This cycling of the magnetic field is what makes a pulsar. The magnetic field of a neutron star is not like the magnetic field of the Earth. The Earth's field is generated by flowing iron in a liquid outer core and is roughly 50 microtesla at the surface, gentle enough that a compass needle follows it. The magnetic field of a neutron star can reach 1 trillion times that strength. In the most extreme cases, objects called magnetars, it can approach 10 quadrillion times Earth's magnetic field strength. strong enough that if a magnetar existed at the distance of the moon, it would erase every magnetic stripe on every credit card on Earth from that distance. More concerning, at that distance, the field would distort the electron clouds around atoms in your body, disrupting the chemistry that allows proteins and DNA to function. A magnetar at the distance of the moon would be lethal not through heat or radiation in the conventional sense, but through fundamental interference with the structure of matter itself. But the neutron star you are near is not a magnetar, it is a standard pulsar, still extraordinary by every measure available to us, but something you can simply observe without imagining the dissolution of chemistry. The magnetic field of this pulsar is misaligned with its rotation axis. This is the key detail. On Earth, the geographic North Pole, the axis around which the planet spins, is not the same location as the magnetic North Pole. They are offset by roughly 11 degrees. Neutron stars have the same kind of misalignment, but the consequences are far more dramatic. Because the magnetic poles are offset from the rotation axis, they sweep around in space with each rotation of the star. And because the magnetic field accelerates charged particles along its polar axis to velocities approaching the speed of light, those particles emit radiation, radio waves, X-rays, gamma rays, in a narrow beam that sweeps through space like a lighthouse beam. Every time that beam sweeps past the Earth, our radio telescopes detect a pulse, regular, precise, rhythmic. From where you are now, you can see both beams, one aimed roughly in your direction as the star turns, the other sweeping away into the galaxy. They are not visible light, they would be invisible to human eyes. But if you could see radio waves, this place would be one of the most precisely rhythmic things in the observable universe. The pulse arrives every 43 milliseconds, and it has been arriving at that interval with that precision for longer than recorded human history. Let that settle. The first pulsar was discovered on the 28th of November, 1967. Jocelyn Bell Burnell, then a graduate student at the University of Cambridge, was working on a newly constructed radio telescope, a 5-acre array of wire and posts she had helped build herself. She noticed an anomaly in the data, a repeating radio signal arriving every 1.3373 seconds, regular to a degree that natural astrophysical sources were not believed capable of producing at the time. The signal was so precise that its discoverers, initially and half seriously, labeled it LGM-1, Little Green Men 1, not because anyone genuinely believed in extraterrestrial origin, but because precision of that degree was simply not expected from the universe. It was the kind of joke scientists make when data is so clean, it looks wrong. It was not wrong. It was a pulsar. The object Bell Burnell had found was later designated PSRB 1919+21. It pulses 0.748 times per second, once every 1.3373 seconds, exactly as she recorded that November. It is still pulsing now as you listen to this, as you settle into your bed, as your breathing slowly deepens, as the room around you holds still and dark. That signal is still arriving at the surface of the Earth, absorbed by the ionosphere, too faint to hear, but real. This was the first evidence that neutron stars were not theoretical. They had been proposed by physicists Walter Baade and Fritz Zwicky in 1934, just 2 years after the discovery of the neutron itself, as the likely remnant of a supernova explosion. For 33 years, they existed only in equations. Then on a strip of paper from a radio telescope in Cambridge, they became fact. You are floating near one of those facts now. The star below you has a thin but meaningful atmosphere. Not an atmosphere like Earth's, no nitrogen, no oxygen, no weather. The atmosphere of a neutron star is approximately 10 centimeters thick. 10 centimeters, the height of a coffee mug. And yet within those 10 centimeters, there is a stratified structure. At the very surface, beneath even that thin atmospheric layer, the crystalline crust begins. The nuclei arranged there are not the ordinary nuclei we find in terrestrial matter. Under the pressure of this gravitational field, nuclei stretch and deform into exotic shapes, rods, sheets, layers, that physicists have nicknamed by geological terms nuclear pasta, gnocchi, lasagna, spaghetti. These are real names used in the scientific literature for phases of nuclear matter that exist nowhere else in the observable universe except inside neutron stars. They form because at these densities, the strong nuclear force, the force that holds protons and neutrons together inside ordinary nuclei, begins to interact with adjacent nuclei, creating structures that blend into one another in ways that no element on the periodic table ever does. Beneath the nuclear pasta layer, the interior transitions into what is called the outer core, a region of neutron-rich matter where the density is approximately twice the nuclear saturation density. This is the density at which ordinary atomic nuclei begin to touch. Below the outer core is the inner core, where densities reach 8 to 10 times that value, and where the equations we have are honest about their own limitations. The universe has places we cannot fully describe. This is one of them. And yet we can measure it from here. One of the most precise tools in all of astronomy is the pulsar, the spinning, radiating remnant, because it tells time better than almost anything else humans have built. The rotation rate of a pulsar is so stable that it was seriously considered as a timekeeping standard in the 1970s. The best millisecond pulsars, those spinning hundreds of times per second, often spun up by accreting material from a companion star, keep time to a precision that rivals atomic clocks. They drift by less than 1 microsecond per year. Some drift by less than 1 microsecond per century. To find an object made of the remnants of stellar death, spinning at hundreds of revolutions per second, radiating beams of radio energy across thousands of light years, and to discover that it tells time more precisely than the best clocks humans have engineered. This is the kind of result that stops physicists mid-sentence. The one you are near is not yet a millisecond pulsar. It is young, only a few thousand years old. Its rotation will slow over millions of years as the pulsar loses energy through its radiation. The energy has to come from somewhere, and it comes from the rotational kinetic energy of the star itself. Every pulse, every sweep of that beam through the galaxy costs the star a fraction of a rotation. Over millions of years, the pulse rate will slow from 23 times per second toward 1 time per second, then slower. Eventually, the pulsar will pass below a threshold, what astronomers call the death line, where its magnetic field and rotation rate are no longer sufficient to generate the radio beams. It will become a quiet, dark, cooling neutron star, invisible to most of our instruments, present but unknown, drifting through the galaxy for billions of years. You are seeing it before that happens. You are here when it is still young enough to scream across the universe. The radio beams sweeping past you are not the only radiation this object emits. X-rays pour from the surface continuously, carrying away the thermal energy of that original collapse. In the vicinity of the magnetic poles, where particle acceleration is most intense, gamma rays emerge, photons of such high energy that each one carries more energy than 1,000,000 visible light photons. The space around this pulsar is not empty in the way that space is usually nearly empty. It is threaded with a wind of relativistic particles, electrons and positrons, streaming outward from the magnetic poles at a significant fraction of the speed of light, inflating a bubble of high-energy plasma around the pulsar that astronomers call a pulsar wind nebula. The most famous pulsar wind nebula is the one surrounding the Crab pulsar, at the center of the Crab Nebula, a supernova remnant in the constellation Taurus. The Crab Nebula is the remains of a supernova that was observed and recorded by Chinese and Arab astronomers in the year 1054 CE. They noted a star so bright it was visible in the daytime sky for 23 days. At night, it was visible for nearly 2 years before fading below naked eye visibility. What they were seeing was the death of a star, a core collapse event releasing more energy in a fraction of a second than the sun will emit over its entire 10 billion year lifespan. At the center of that expanding cloud of debris, a pulsar now spins 30 times per second, driving a wind of particles that illuminates the nebula from within. When the Hubble Space Telescope photographs the Crab Nebula, what it captures is not just ancient debris, it is the ongoing, present-tense activity of a neutron star that has been spinning and radiating for nearly 1,000 years since the Chinese court astronomers first marked it in their records. You are in a place like that now. The nebula around you is younger, slightly dimmer, still dense with the ejecta of the original explosion. Fingers of gas stretch outward in all directions, still warm enough to glow. The pulsar at the center, the one you are nearest, is powering this glow from within, its wind of particles crashing into the surrounding gas and energizing it. The light coming from this nebula will reach Earth in a few thousand years. When it arrives, human astronomers, or whatever beings are watching the sky at that time, will see a brightening in the radio and X-ray sky. They will aim their instruments at it and begin to measure. They will find at the center a pulse, regular, precise, rhythmic, and they will know that something ended here once, and something extraordinary was left behind. The universe does not waste the deaths of stars. The star is rotating beneath you, its magnetic field sweeping through you every 43 milliseconds. The X-ray glow is faint but constant. The radio beams reach outward in 2 directions, one briefly passing through the volume of space you occupy before continuing on into the galaxy. Your body, if it were here, if this were somehow possible, would be bathed in radiation, threaded with magnetic field, positioned at the edge of one of the most extreme gravitational wells in the observable universe. And yet there is also something still about it. The pulsar does not announce itself with sound. It does not vibrate the space around it in any way you could feel. It turns. It radiates. It tells time. It has been doing this since long before any human being was born, and it will continue long after the last star in the galaxy has gone dark. Lie still now. The pulse continues. 43 milliseconds between each sweep. 43 milliseconds. Your breath is slower than that. One breath takes perhaps 3 or 4 seconds, roughly 70 pulses of this star, 70 precise measured beats for every breath you take. The star does not know you are here. It does not need to. It is simply doing what neutron stars do, what physics requires them to do, what the conservation of angular momentum and the geometry of magnetic fields and the properties of charged particles in extreme fields have been producing since the first supernova of this kind detonated in the early galaxy, billions of years ago. Let the rhythm of it carry you. The pulse, now, and now, and now, and now. The sound of it, if sound existed here, would be a high, steady tone, 23 beats per second, just above the threshold of human hearing. Your nervous system evolved to detect sounds in that range as meaningful, as signal rather than noise, would parse it as music of a kind. Not the music of instruments or intention, but the music of physics operating without interruption for thousands of years in the cold of interstellar space. The pulsar wind, that outflowing stream of relativistic particles, does not travel uniformly in all directions. It is shaped by the magnetic field, stronger along the equatorial plane of the pulsar and more focused toward the poles. As the wind crashes into the surrounding nebula, it creates a termination shock, a boundary where the wind slows from relativistic speed to non-relativistic speed, converting kinetic energy to heat and radiation. Inside the termination shock, the wind is compressed and turbulent. Outside it, the nebula plasma is heated and illuminated. The Crab Pulsars Wind Nebula has been imaged in X-rays by the Chandra X Ray Observatory, and what the images reveal is not a smooth, symmetric blob of glowing gas. It is structured. There is a bright ring around the pulsar, the termination shock itself, glowing in X-rays at a radius of roughly a third of a light year. There are jets extending from the poles, collimated by the magnetic field, into narrow streams of X-ray emission stretching outward for a light year or more. And within the wind there are dynamic structures, wisps and knots of brightness that move and change over periods of months and years, driven by instabilities in the relativistic flow. The Crab Nebula is not a static relic. It is an active, dynamic structure driven by a pulsar that has been spinning and radiating for approximately 970 years. The nebula around you is younger, less organized. The termination shock exists, but is less well defined. The jets are forming, but not yet fully collimated. This is a pulsar wind nebula in its early history, still being shaped by the object at its center. You are watching the architecture of astrophysical extremity being assembled. It takes time to let that in. The human brain is not designed to parse structures measured in light years and timescales measured in millennia. We evolved to track the movement of animals across a landscape, the ripening of fruit, the approach of storms. The scales of astrophysics require deliberate recalibration of what counts as near and what counts as fast. A jet of X-ray emitting plasma stretching 1 light year from a neutron star is, to the jet, moving at a significant fraction of the speed of light. To a human observer, it looks like a frozen structure in an image. The motion is there, in the data in the time-lapse comparisons between Chandra images taken months apart, but it is not visible in the way a thrown stone is visible. The universe moves, but on scales that require instruments to see. Your instruments tonight are not telescopes. They are the capacity for patient attention. 43 milliseconds. The beam sweeps through, carries its radio energy through the surrounding nebula, exits into open space, continues outward at the speed of light, 300,000 kilometers per second, and begins the long journey toward whatever is listening in this direction. Radio pulses from the nearest known pulsars take hundreds to thousands of years to reach Earth. They travel through the interstellar medium, which is not quite empty. It is threaded with a thin plasma of free electrons, roughly 1 electron per 10 cubic centimeters. This plasma has a measurable effect on radio waves. Lower frequency radio waves travel slightly slower through the plasma than higher frequency ones, causing the pulse to arrive spread out in time, with lower frequencies arriving later. The degree of this spread, called dispersion, allows astronomers to calculate the dispersion measure of a pulsar, which is proportional to the integrated electron column density between us and the source. It is, in effect, a measurement of how much ionized gas lies between the pulsar and our instruments. Combined with models of electron density in the galaxy, the dispersion measure can be used to estimate the pulsar's distance. This is how we map pulsars we cannot image, not by seeing them directly, but by measuring the delay in their signal. The pulsar you are near has a dispersion measure that corresponds, using the best available models of the galactic electron density, to a distance of approximately 8,000 light-years from Earth. 8,000 light-years. The radio waves currently leaving this pulsar will arrive at Earth in approximately 8,000 years. The astronomers who will detect this pulse are not yet born. The civilization that will build the instruments to receive it may not yet exist, and yet the pulse is already traveling. It is in the interstellar medium right now, spreading outward at the speed of light, carrying the precise timing signature of this object through the thin plasma of the galaxy. It is patient. It will arrive. Everything the pulsar sends outward, it sends without expectation of reply. The universe transmits. The universe does not wait for acknowledgement. There is something in that worth carrying with you into sleep. The human experience of the night is often characterized by waiting, for sleep that does not come immediately, for thoughts that do not quiet on demand, for the body to relax its vigilance and allow itself to be still. The pulsar does not wait for stillness. It produces its signal continuously, indifferent to whether any instrument is positioned to receive it. The signal exists. It travels. That is sufficient. Whether it is detected is a matter of geometry and timing, of whether a radio telescope on a spinning planet in a particular galaxy happens to be oriented correctly when the beam arrives. Most pulsar beams do not cross Earth at all. The beams are narrow, typically only a few degrees wide, and the probability that any given pulsar's beam sweeps across the Earth depends on the orientation of the magnetic axis relative to Earth's position. Most pulsars in the galaxy are invisible to us, not because they are not pulsing, but because their beams simply do not point in our direction. We see the universe through a narrow keyhole. What exists on the other side of that keyhole is real, regardless of whether we have managed to look through it yet. The neutron star you are near exists inside a galaxy that has been forming stars for over 13 billion years. The Milky Way contains somewhere between 100 billion and 400 billion stars. Of all those stars, the ones massive enough to end their lives in core collapse supernovae, the kind that produce neutron stars, represent a fraction of a percent of the total stellar population. And yet, over that span of time, the number of supernovae that have occurred within the Milky Way alone is estimated at somewhere between 100 million and 1 billion events, each one potentially leaving behind a neutron star, or in cases where the remnant mass exceeded roughly 2 to 3 solar masses, a black hole. The galaxy is not the peaceful star-scattered structure it appears to be from Earth's night sky. It is the aftermath of extraordinary violence, measured across geological and astronomical timescales, its most extreme remnants scattered throughout its disk and halo like seeds of collapsed physics. You are near one of those seeds. The neutron star has a companion, Not every pulsar does. Some exist in isolation, the single remnant of a solitary stellar death, but this one orbits with a dim, cool star approximately twice the mass of the Sun. The companion is still alive in the conventional sense. It is still fusing hydrogen in its core, still generating the outward pressure that keeps it from collapsing. But it is aging. Over hundreds of millions of years, it will expand into a red giant, and when it does, its outer layers will begin to overflow the gravitational boundary between the two stars, a theoretical surface called the Roche lobe, and material will begin to flow toward the neutron star. That process has not yet begun. For now, the two objects simply orbit each other. The neutron star completes one orbit around its companion every 6 hours and 12 minutes. At the closest point in its elliptical orbit, the separation between them is approximately 3 million kilometers, about 8 times the average distance between the Earth and the Moon. At the farthest point, the separation grows to nearly 9 million kilometers. As the neutron star passes through different distances from its companion, the companion's gravity causes measurable changes in the pulse timing. The arrival time of each radio pulse shifts by microseconds as the neutron star moves toward or away from Earth in its orbit, a phenomenon described by the Doppler effect and first used by radio astronomers to map the orbital geometry of binary pulsar systems in exquisite detail. The first binary pulsar was discovered in 1974 by Russell Hulse and Joseph Taylor at the Arecibo Radio Observatory in Puerto Rico. The system, designated PSRB 1913+16, consists of a pulsar and a second neutron star orbiting each other every 7.75 hours. Over decades of monitoring, Hulse and Taylor observed something remarkable. The orbital period was decreasing. The two neutron stars were gradually spiraling inward toward each other. The rate of this decay matched, to within 0.5%, the predictions of general relativity for a system losing energy through gravitational wave emission. This was the first indirect evidence for gravitational waves, ripples in space-time itself, spreading outward from accelerating masses, 17 years before the LIGO detector would directly observe them for the first time in 2015. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. The binary pulsar system you are near will one day follow a similar path. In hundreds of millions of years, or sooner if the companion star expands and begins transferring mass, spinning the pulsar up into a millisecond pulsar, the orbital dynamics will shift, the separation will change, the pulse timing will evolve. But for now, the orbit is stable, the companion is ordinary, and the pulsar turns 23 times per second in the dark. You are watching a slow story, one that takes hundreds of millions of years to reach its next chapter. Let us talk about what happens when neutron stars are not quiet. On December 27, 2004, one of the most energetic events ever detected from within our galaxy arrived at Earth. It came from a magnetar, SGR 1806-20, located approximately 50,000 light-years away, near the center of the Milky Way. What reached Earth was a burst of gamma radiation so intense that it was detectable by spacecraft designed to observe high-energy events across the universe. For a fraction of a second, this single object, this one neutron star, released more energy in gamma rays than the Sun will emit across its entire 10 billion year lifespan. Some estimates suggest the burst, lasting approximately 0.2 seconds, released more energy than the Sun produces in 250,000 years. The event caused measurable ionization in Earth's upper atmosphere at a distance of 50,000 light-years. This was a magnetar flare. Magnetars are a subclass of neutron stars with magnetic fields so extreme, reaching 10 to 100 quadrillion times Earth's magnetic field, that the field itself becomes structurally significant. In ordinary matter, magnetic fields influence electrons and affect chemistry, but the underlying structure of atoms is not altered. In the crust of a magnetar, the field is strong enough to distort the crystalline structure of nuclear matter itself. The crust is under constant magnetic stress. Occasionally, that stress exceeds the yield strength of the crust, and the crust fractures, a starquake. The fracture releases stored magnetic energy in an explosive burst of X-rays and gamma rays. The scale of these events relative to the size of the object producing them is almost impossible to contextualize. A starquake on a neutron star involves a displacement of the crust by perhaps a millimeter or less on a 20-kilometer object, and yet the energy released is equivalent to centuries or millennia of solar output. The neutron star you are near is not a magnetar. Its field, while still roughly 1 trillion times stronger than Earth's, is in the range typical of a young newly formed pulsar. But starquakes, or glitches as astronomers call the rotational effects they produce, do happen here. A glitch is a sudden small increase in a pulsar's rotation rate. They are brief and unpredictable. One day the pulsar is spinning at its steady 23.0000 rotations per second, and then, without warning, it spins slightly faster. The change is tiny, perhaps 1 part in 10 million. But for an object whose stability and precision we rely on for some of our most refined measurements, a sudden change in rotation rate is scientifically jarring, the way a perfect clock suddenly running a microsecond fast would be jarring to a clockmaker. The cause of pulsar glitches is believed to involve the interior structure of the neutron star. Inside the outer core, neutrons are not simply packed together like static balls. Under the conditions of temperature and density inside a neutron star, neutrons form a quantum mechanical state called a superfluid, a phase of matter in which viscosity becomes zero and flow encounters no friction. The superfluid neutrons form vortices, thin threads of rotating quantum fluid, whose spacing encodes the rotation rate of the neutron star. As the outer crust of the star spins down slightly due to energy loss from radiation, it can decouple from the superfluid interior. The superfluid continues rotating at its previous rate. When the two components suddenly couple again, when angular momentum transfers from the fast-spinning superfluid to the slower outer crust, the crust briefly spins up. This appears from outside the star as a glitch. You cannot see the glitch from here. You can only count pulses. But in the data collected by radio telescopes on Earth, the glitch leaves an unmistakable signature, a step function in the pulse timing record, followed by a gradual recovery over days or weeks as the star relaxes. Astronomers monitoring the Vela pulsar, a well-studied young pulsar approximately 1,000 light-years from Earth, have recorded more than 100 glitches since systematic monitoring began. The Crab pulsar has glitched roughly 24 times in the same period. Each glitch is a message from the interior, from the superfluid core where our theories reach their limits. The star is speaking to us from inside itself in the only language available, a slight change in the timing of its pulse. When a massive star ends its life in a core collapse supernova, the explosion is not symmetric. The collapsing core does not fall inward and then rebound uniformly in all directions. There are instabilities in the collapsing material asymmetries in the neutrino flux that carries away an enormous fraction of the explosion's energy, and turbulent convection in the proto-neutron star that forms in the first fraction of a second. The result is that the explosion is uneven, and the neutron star that forms receives a kick, a natal kick, that sends it moving through space at velocities ranging from a few hundred to more than 1,000 kilometers per second. Some neutron stars have been observed with space velocities exceeding 1,500 kilometers per second. These are called hypervelocity neutron stars, and they are moving fast enough to eventually escape the gravitational pull of the Milky Way entirely, exiting the galaxy and drifting into the intergalactic void. The neutron star you are near received a kick at birth. It is moving through the galaxy at approximately 400 kilometers per second, relative to the surrounding stellar population, fast enough to cross the distance between the Earth and the Moon in about 15 minutes. And yet, on a galactic scale, this velocity is modest. The galaxy is 100,000 light-years across. Moving at 400 kilometers per second, the neutron star would take roughly 70 million years to cross it. Its trajectory is a long, gradual arc, shaped by the gravitational field of the galaxy's combined mass, slowly curving through the disk and perhaps eventually settling into a stable orbit around the galactic center. You are riding alongside it now. The motion is not perceptible, the way the motion of a car or a train is perceptible. There is no sensation of speed. There is only the gradual, almost geological shifting of position relative to the background stars, measured over centuries, apparent only in the accumulated data of proper motion catalogs. This is how most cosmic motion feels, from inside it, vast and imperceptible. In some cases, neutron stars are born in binary systems, pairs of massive stars that form together from the same gas cloud, orbiting each other before either of them died. When the more massive star explodes first, the resulting neutron star may remain gravitationally bound to its companion, provided the supernova kick does not disrupt the orbit. The companion eventually evolves, expands, transfers mass, possibly explodes in its own supernova, and if the system survives both explosions, what remains is a double neutron star binary, two neutron stars orbiting each other. This is not a rare accident. These systems exist. We have found them. Two dead stars, each the compressed remnant of something that once burned, orbiting each other in the dark. The first double neutron star system ever confirmed was PSR B 1913+16, the Hulse-Taylor binary. Since then, more than a dozen others have been cataloged. Each one is a ticking clock in a double sense. It pulses with the regular rotation of the pulsar component, and it also spirals inward, slowly, as energy is lost to gravitational wave emission. The in-spiral is gradual. For PSR B 1913+16, the two neutron stars will merge in approximately 300 million years. Other double neutron star systems have shorter merger timescales, some less than 100 million years. In the context of cosmic time, these are not distant futures. The universe is 13.8 billion years old. 300 million years is roughly 2% of its current age. The universe has already lived long enough to have seen an enormous number of these mergers occur. Let us go to one. We are going to move to a different place, a place in the galaxy where a merger has just happened. This event concluded perhaps 30 seconds ago, and its light and radiation are still expanding outward from the site. The gravitational waves from the final in-spiral and merger have already passed through you. They moved at the speed of light, arriving and departing before you could have noticed, stretching and compressing the fabric of space-time by a distance far smaller than the diameter of a proton as they passed. What remains is something that astronomers call a kilonova. The two neutron stars, in the final minutes before merger, were orbiting each other hundreds of times per second, a rate that increased as they drew closer and gravitational wave emission accelerated the in-spiral. In the final milliseconds, they were orbiting thousands of times per second, separated by only a few kilometers. Then they touched. The outer layers of each star, the crystalline neutron-rich crust, made contact and were disrupted. Material was flung outward by tidal forces at a significant fraction of the speed of light. The stars merged into a single, violently rotating object, perhaps a hypermassive neutron star lasting milliseconds before collapsing into a black hole, or perhaps a stable massive neutron star if the combined mass remained below the maximum. The physics of what happens in that first second is one of the most complex problems in computational astrophysics. What concerns us tonight is what happens in the seconds and hours and days after. The material flung outward during the merger, the tidal ejecta, is extraordinarily neutron-rich. Ordinary matter in the universe has roughly equal numbers of protons and neutrons in its atomic nuclei. The crust and core of a neutron star are, by definition, composed almost entirely of neutrons. When that material is suddenly decompressed, when it escapes the enormous pressure of the neutron star's interior and expands into the surrounding space, the neutrons begin decaying. A free neutron, not bound inside an atomic nucleus, has a half-life of approximately 14 minutes and 38 seconds. It decays into a proton, an electron, and an antineutrino. As the neutron-rich ejecta expands, this decay begins to create proton-rich conditions in some regions, while other regions remain neutron-saturated long enough for something extraordinary to happen. The extraordinary thing is called the RU process. RAR stands for rapid. The R process is a sequence of rapid neutron capture reactions, a scenario in which atomic nuclei absorb neutrons so quickly, faster than the captured neutrons can decay, that they build up to mass numbers far higher than can be achieved through any other process in the universe. The ordinary stellar nucleosynthesis that produced the carbon and oxygen in your body stops at iron 56, the most tightly bound nucleus, the end of the energy-releasing fusion chain. Elements heavier than iron require the addition of energy, not the release of it. In the core of a star, there is not enough free neutron flux, sustained for long enough, to drive nuclear masses up to gold, or platinum, or uranium. But in the neutron-rich ejecta of a neutron star merger, expanding at a fraction of the speed of light, with neutron densities orders of magnitude higher than anything achievable in a stellar interior, the R process runs. Within seconds to minutes of the merger, atomic nuclei are being built that did not exist anywhere in the ejecta cloud a moment before. Nuclei with mass numbers of 190, 200, 230, unstable, neutron-rich, decaying rapidly through beta decay toward their stable configurations. Within hours, the cloud of ejecta begins to glow, not in visible light initially, in infrared, as the radioactive decay of freshly synthesized heavy nuclei releases energy into the expanding gas. This glow is a kilonova. The merger of two dead stars produces in its aftermath the gold that exists in the universe. Your gold, if you are wearing any. The gold in every ring, in every circuit board, in every device in your home. On August 17, 2017, the LIGO and Virgo gravitational wave detectors simultaneously detected a gravitational wave signal designated GW170817. Unlike the previous gravitational wave detections, which had the sharp, brief chirp characteristic of merging black holes, GW170817 lasted approximately 100 seconds in the detector band, a longer signal consistent with the slower, lower mass in-spiral of two neutron stars. Within 2 seconds of the gravitational wave signal's end, NASA's Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same sky location. 70 observatories on 6 continents and in space turned toward the coordinates within hours. What they found in the galaxy NGC 4993, approximately 130 million light-years from Earth, was a new point of light that had not been there before. Over the following days, the spectrum of that light was analyzed by instruments, including the European Southern Observatory's Very Large Telescope in Chile. The spectral lines were shifted, broadened, and structured in ways that matched the theoretical signatures of process nucleosynthesis, of rapid neutron capture, building heavy elements in real time. Strontium was identified with high confidence. Signatures consistent with other heavy process elements, including those in the lanthanide series, were present. Estimates of the total mass of gold produced in this single event, one pair of merging neutron stars, ranged from a few percent of a solar mass to perhaps 10% of a solar mass. The gold in your wedding ring, if you have one, the gold in the thin connectors inside the phone or computer or tablet you may be holding or have nearby, all of it traced back through the formation of the solar system 4.5 billion years ago, through the mixing of the interstellar medium, through the supernovae that dispersed it, through the kilonovae that created it. All of it carries the signature of neutron star mergers. You are made in part of events like the one that just happened 30 seconds ago, in the space you have entered. The violence that made the gold also made the silence you are resting in. The kilonova expanding around you is not uniform. The tidal dynamical ejecta, material stripped from the neutron stars during the final in-spiral, forms a roughly toroidal distribution around the merger site, concentrated near the equatorial plane. Above and below the poles, a magnetically and neutrino-driven wind from the remnant moves slightly faster, forming a roughly spherical outer shell. The two components have different compositions. The tidal ejecta is extremely neutron-rich and produces the heaviest process elements, including those in the lanthanide series, which are responsible for the infrared opacity that causes the kilonova to glow red in the days following the merger. The wind component is less neutron-saturated and produces lighter process elements, including strontium and possibly some of the platinum group metals. The entire event will fade over the course of weeks. Unlike a supernova, which can remain visible for months or even years, a kilonova dims rapidly as the radioactive heating decays. Within a month, this one will have faded below the detection threshold of all but the most sensitive instruments. The universe does extraordinary things quietly. Short gamma ray bursts were observed and cataloged for decades before astronomers understood what produced them. They were detected, their sky positions recorded, and their afterglows monitored. But the progenitor, the source, was unknown. Theoretical models proposed neutron star mergers as early as 1986, but confirmation required a coincident gravitational wave and electromagnetic detection. GW170817 was that confirmation. In the weeks following the detection, More than 3,000 astronomers published or co-authored papers analyzing the data from that single event. It was, by some measures, the most observed astrophysical event in history. The coincident arrival of the gravitational wave and the gamma-ray burst, separated by 1.74 seconds, possibly due to the time required for the jet to break free of the merger debris, also placed the most precise constraint ever obtained on the difference between the speed of gravitational waves and the speed of light. The difference, if any, is less than 3 parts in 10 to the 15th power. Gravitational waves and light travel at the same speed, to a precision that rules out many alternative theories of gravity. A single observation, a single pair of dead stars in a galaxy 130 million light-years away, producing a collision that lasted milliseconds, lit up in the kilonova that followed, and in doing so confirmed the origin of gold, constrained the equation of state of dense nuclear matter, verified the speed of gravitational waves, explained the origin of short gamma-ray bursts, and placed limits on alternative theories of gravity. This is what neutron stars are for in the economy of physics. The remnant at the center of this cloud, whether it is a black hole or a surviving neutron star, spins. If it is a neutron star, it spins very fast. The conservation of angular momentum applied to the combined angular momentum of the inspiraling system means that any surviving neutron star would be rotating thousands of times per second. You are sitting with uncertainty about which it is, the way physicists sit with it, not as absence, but as the current edge of knowledge. Let the not knowing be restful rather than unsettling. The universe has been carrying questions inside it longer than any civilization has existed to ask them. It is comfortable with the unanswered. You can be too. In the expanding shell of freshly synthesized heavy elements, atoms are finding the electrons they need to complete their structure, transitioning from the hot ionized plasma of the first minutes into the cooler, neutral atoms that will eventually disperse into the interstellar medium of their host galaxy, and in 4.5 billion years, perhaps find themselves inside a forming solar system, incorporated into a planet, dissolved into an ocean, incorporated into living cells, and eventually worn as jewelry by a being who will lie awake at night wondering about the origin of things. This is not poetry imposed on the facts. This is the actual pathway that the gold in your body has traveled. You are the end of a very long chain that began at an event like this one. We are going to leave the merger site now. We are going somewhere that represents a later chapter in the neutron star life cycle. Not the beginning, not the violent middle, but the long, quiet transformation that follows. We are going to a millisecond pulsar. A young pulsar, like the one at the beginning of tonight's journey, is spinning fast and slowing down. Energy pours out through the radio and X-ray beams. Over millions of years, the rotation slows. The pulse rate drops from hundreds of times per second to once per second to once every few seconds. Eventually, after perhaps tens of millions to a few 100 million years, the rotation rate drops below the death line, the threshold below which the pulsar mechanism can no longer operate. The magnetic field, which has also been decaying over this time, can no longer accelerate particles to produce the coherent radio beam. The pulsar turns off. What remains is a quiet, cooling neutron star, a neutron star that no longer pulses, no longer emits significant radiation, and is detectable only through its thermal X-ray emission, which itself fades over billions of years as the star cools. This would be the end, if not for the companion. In a binary system where the neutron star has been orbiting a lower mass companion, a star perhaps half the mass of the Sun, the companion has a longer lifespan than the original massive progenitor. As the companion exhausts its core hydrogen and begins to transition toward a red giant phase, its outer layers expand. If the expansion is large enough that the companion's outer atmosphere approaches the Roche-Lobe boundary, the gravitational tidal surface that marks the edge of the neutron star's gravitational dominance, material begins to transfer. A stream of gas flows from the companion toward the neutron star. This process is called accretion. The infalling material carries angular momentum. As that material falls onto the neutron star's surface, it deposits that angular momentum into the star. The neutron star, which had been spinning slowly and silently, begins to spin up. The accretion disk, a flat, hot structure of spiraling infalling gas that forms around the neutron star before the material finally reaches the surface, glows in X-rays. The system becomes what astronomers call a low-mass X-ray binary. Systems of this kind are among the brightest X-ray sources in the sky. Over millions to hundreds of millions of years, the accretion slowly deposits enough angular momentum to spin the neutron star up from once per second to hundreds of times per second. The companion star, meanwhile, transfers much of its outer mass. The magnetic field of the neutron star, buried under the accreted material, is partially screened and decays to a lower value, typically 100 to 1,000 times weaker than a young pulsar's field. When the accretion eventually stops, what remains is a neutron star spinning hundreds of times per second with a relatively weak magnetic field and a white dwarf companion. This is a millisecond pulsar, a recycled pulsar, an old dead star that was spun back up to extraordinary speed by millions of years of patient accretion. The universe found a way to give the dead star its precision back, not through explosion or energy, but through patience, through the slow, steady transfer of angular momentum over millions of years. The millisecond pulsar you are now approaching is designated PSR J0030 plus 0451, a real object approximately 350 light-years from Earth, one of the closest known millisecond pulsars. It spins at approximately 205 times per second. In 2019, the NICER instrument aboard the International Space Station, a soft X-ray telescope mounted in Earth orbit, observed this pulsar for months, accumulating enough X-ray photons to map the temperature distribution of the neutron star's surface with unprecedented precision. What NICER found overturned a long-standing assumption. Before NICER, models of millisecond pulsar emission assumed that the hotspots, the regions of the surface heated by infalling particles channeled by the magnetic field, would be located at the magnetic poles, which were assumed to be roughly antipodal, one hotspot in the northern hemisphere, one in the southern hemisphere, roughly opposite each other. What NICER found for PSR J0030 plus 0451 was different. The hotspots were both located in the southern hemisphere. One was roughly circular, the other was elongated, crescent-shaped, and both were displaced far from the geometric antipodal positions a simple dipole model would predict. The magnetic field geometry of this pulsar is not a simple dipole. It is more complex, possibly a multipole field, with contributions from higher-order magnetic structures near the surface. This result, derived from counting individual X-ray photons arriving at a detector in Earth orbit from a neutron star 350 light-years away, is one of the most precise measurements of neutron star surface geometry ever made. It also simultaneously constrained the mass and radius of the neutron star. NICER derived a radius of approximately 12 to 13 kilometers and a mass of approximately 1.3 to 1.4 solar masses. Every X-ray photon that NICER counted had traveled 350 light-years to reach the detector. Each one left the surface of this neutron star 350 years ago during the 17th century by Earth's historical calendar, and arrived by chance at the precise location in Earth orbit where an instrument had been placed to count it. You are at the source now. You are at the surface of PSR J0030 plus 0451, 350 light-years from Earth, in the year those photons are departing. The surface is not the stark, uniform crystalline structure of a young pulsar. It is older. The field lines are more complex. The hotspots glow in X-rays at regions that a simple model would not have predicted. One roughly circular, roughly 700 meters across, warm and constant. The other elongated, stretched across more than a kilometer of crust, crescent-shaped, glowing in a slightly different temperature band. If you could see X-rays the way you see visible light, these two regions would be distinct, identifiable features on the surface of an object smaller than a city. The star is spinning 205 times per second. In the time it takes to draw one slow breath, approximately 4 seconds, it has rotated more than 800 times. The centripetal forces on the equatorial surface are significant. The equatorial radius of a millisecond pulsar is slightly larger than its polar radius because the rapid rotation causes the star to bulge slightly at its equator. The degree of this oblateness is measurable and provides additional constraints on the equation of state of the interior. Everything about this object is measurable, everything is precise, and yet the interior, the core, the phase of matter at the center, remains beyond the reach of current theory, written in a language of density and pressure that our equations can approach but not fully enter. There is a center to this object that we have never seen and cannot yet fully describe, and yet we know it is there because the X-rays from its surface have been falling on our instruments for years, telling us its mass, its radius, the shape of its magnetic field, the temperature of its hotspots. The evidence surrounds the mystery without dissolving it. A millisecond pulsar, spinning hundreds of times per second with a rotation rate that drifts by less than a microsecond per year, is an extraordinarily stable clock, a network of millisecond pulsars distributed across the sky, monitored by radio telescopes for years or decades, forms what is called a pulsar timing array. The principle is straightforward. If each pulsar is a clock, and if something perturbs the space-time between a pulsar and the Earth, the pulse arrival times will shift slightly. A gravitational wave passing through the galaxy would stretch space-time in one direction and compress it in the perpendicular direction, causing some pulsars in the array to appear to pulse slightly early and others to appear to pulse slightly late in a characteristic pattern correlated across the sky. In 2023, multiple independent pulsar timing array collaborations, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array, simultaneously reported evidence for a gravitational wave background. Not a single event like GW170817, but a diffuse background hum of gravitational waves arriving from all directions. The signal appeared as correlated variations in pulse timing across dozens of millisecond pulsars, monitored for 15 or more years. The pattern of correlations followed a specific curve called the Hellings-Downs correlation, the expected signature of an isotropic stochastic gravitational wave background. The most likely source of this background is a population of supermassive black hole binaries, pairs of black holes each billions of solar masses in size, at the centers of merging galaxies throughout the observable universe, producing gravitational waves as they slowly spiral inward. The millisecond pulsars of the timing array are detecting the combined gravitational wave output of black hole pairs throughout the observable universe. The clocks are picking up the tremor of the cosmos, a background vibration produced by events at the centers of distant galaxies, arriving as a barely perceptible correlation in the pulses of dozens of dead stars scattered across the sky above Earth. A dead star, born in a supernova explosion hundreds of millions of years ago, slowly died as a pulsar, was resurrected by millions of years of accretion from a companion star, was spun up to hundreds of rotations per second, and now serves as one detector in a network sensitive to gravitational waves from merging supermassive black holes billions of light years away. The neutron star did not evolve toward this function. Physics arranged it this way. The same physics that governs nuclear forces and angular momentum and gravitational wave emission and magnetic field decay happened to produce an object whose natural behavior, steady, precise rotation, is useful as a gravitational wave detector when arrays of them are assembled and monitored. The universe did not plan the pulsar timing array, but the pulsar timing array works. The star beneath you has been through more than most objects in the universe. It was born in fire. It spun down slowly over millions of years. It grew cold and quiet. Then a companion offered it angular momentum, and it woke up again, spinning faster than it had ever spun in its youth. It is now, in a sense, more active than it was when it was young, carrying more rotational kinetic energy, serving more purposes, contributing more precisely to our understanding of the universe than a young, loud, violently radiating pulsar ever could. It aged into usefulness. The oldest, most spun up, most precisely timed neutron stars, the ones that have lived long enough to be recycled and steadied, are the ones that tell us the most. Lie still, let the rotation of this star carry you, 205 times per second, perfectly steady, monitored by instruments on Earth every day, contributing its pulse to a catalog that spans decades. You are a system of extraordinary precision too. Not the precision of a pulsar, nothing organic reaches that, but the precision of a complex biological system that has been refined over 4 billion years of evolution, adapted to exactly this environment, exactly this temperature, exactly this darkness, exactly this moment of rest. Rest is not a pause in the system, it is part of the system. In, out, the pulsar turns, the hotspots glow, the X-rays travel toward Earth, the timing residuals accumulate in the dataset, and somewhere in the pattern of those residuals, a faint correlation is emerging with the timing residuals of other pulsars scattered across the sky. The tremor of distant black holes passed through space-time, picked up by the patient precision of recycled dead stars. The universe is full of instruments we did not build. Tonight's final journey takes us to the most extreme members of this family. We are going to a magnetar. The neutron stars you have been near tonight have magnetic fields that, by the standards of terrestrial physics, are incomprehensibly strong. A young pulsar's field strength of roughly 10 billion Tesla, 1 trillion times Earth's field, is already far beyond any magnetic field achievable in a laboratory. But a magnetar's field is stronger still by a factor of 1,000 to 10,000. Magnetar field strengths reach 10 to 100 quadrillion times Earth's field, expressed in scientific notation as 10 to the power of 15 Tesla at the surface. At these field strengths, the structure of matter itself is altered. In ordinary matter, the electron orbitals around atomic nuclei are nearly spherical, slightly perturbed by the presence of other atoms and molecules. As field strength increases, the magnetic force begins to compete with, and eventually dominate, the Coulomb force, the electromagnetic attraction between the negatively charged electron and the positively charged nucleus. At field strengths above roughly 10 billion Tesla, electron orbitals are compressed perpendicular to the magnetic field. Atoms become elongated, cigar-shaped, extending along the field lines. Chemistry is affected. Materials that would be liquid or gaseous under normal conditions adopt crystal-like structures aligned with the field. At magnetar field strengths, this effect is so extreme that atoms, if they could exist in that environment at all, would be stretched to aspect ratios of 1,000 to 1. The vacuum itself at these field strengths is no longer optically neutral. At fields above approximately 4 times 10 to the power of 13 Tesla, a process called vacuum birefringence becomes significant. The quantum mechanical fluctuations of the vacuum, the constant creation and annihilation of virtual particle-antiparticle pairs, are polarized by the magnetic field, causing the vacuum to have different refractive indices for different polarizations of light. Light traveling through the magnetosphere of a magnetar bends differently depending on its polarization, the way light bends differently in a crystal whose refractive index depends on direction. Vacuum birefringence was predicted by quantum electrodynamics in the 1930s. It was first observationally confirmed in 2016 using the ESO Very Large Telescope's FIROS-2 instrument to observe linearly polarized optical light from the neutron star RX J1856.5-3754. The degree of polarization detected was higher than could be explained by the emission processes alone, matching the prediction of vacuum birefringence in the strong magnetic field of the neutron star. The universe is a laboratory for physics we cannot yet replicate on Earth, and the magnetar you are approaching is the most extreme version of that laboratory. You are approaching a place where the vacuum itself has been changed by the presence of a magnetic field. The magnetar you are near is designated SGR 1935 plus 2154, a real object located approximately 30,000 light-years away in the constellation Vulpecula. It is a soft gamma-ray repeater, one of a class of objects that periodically emits bursts of gamma radiation and X-rays from its surface, driven by starquakes in its magnetically stressed crust. On April 28, 2020, this magnetar did something no magnetar had ever been confirmed to do before. It emitted a radio burst. Not just any radio burst, a burst so bright, so short, and so structured that it was detected by the CHIME radio telescope in Canada and the STARE-2 instrument in California simultaneously. The burst lasted approximately 1 millisecond. Its brightness temperature, The equivalent blackbody temperature needed to produce a thermal source of the same brightness at that frequency was approximately 10 to the power of 36 Kelvin. This is not a temperature anything physically has. It is a measure of brightness that implies coherent emission, not thermal photons from a hot surface, but organized, coordinated electromagnetic radiation produced by charged particles moving in concert, the way a laser produces coherent optical light through stimulated emission. The burst from SGR 1935 plus 2154 was the first radio burst ever detected from a known magnetar, and its properties were consistent with a class of phenomena that had puzzled astronomers since 2007, fast radio bursts. Fast radio bursts are millisecond duration radio pulses of enormous luminosity detected from cosmological distances, hundreds of millions to billions of light years from Earth. The first one was discovered in archival data from the Parkes Radio Telescope by Duncan Lorimer and his student David Narkovich in 2007. Since then, the CHIME telescope, with its wide field of view and continuous sky monitoring, has detected thousands. Some fast radio bursts repeat. The same sky location produces multiple bursts, sometimes in clusters separated by days or weeks. Their origin was unknown until SGR 1935 plus 2154 provided the first concrete link to magnetars, a magnetar in our own galaxy, producing a burst with properties matching extragalactic fast radio bursts, strongly implicates magnetar activity as at least one mechanism, perhaps the primary mechanism, for producing fast radio bursts in other galaxies. The magnetar you are near has cousins in distant galaxies, producing flashes visible across the observable universe, millisecond events of radio brightness so extreme that they illuminate the intergalactic medium as they travel through it. You are floating near the surface of SGR 1935 plus 2154 now. The surface is hot, hotter than the young Pulsar's surface, because the magnetic energy that is constantly being deposited into the crust through the stresses of the decaying, shifting field heats it from within. The surface temperature is approximately 5 million Kelvin. The magnetic field permeates the interior and the exterior, connecting the core to the magnetosphere, the region of space around the star filled with plasma and field lines. The magnetosphere is not quiet. Currents flow in the magnetosphere, twist the external field, build up stress, and occasionally reconnect in events that release energy suddenly. The magnetosphere of a magnetar is filled with plasma, electrons and positrons accelerated by the enormous field to velocities close to the speed of light. In the standard model of a pulsar magnetosphere, developed first by Peter Goldreich and William Julian in 1969, the magnetosphere rotates rigidly with the star out to a boundary called the light cylinder, the radius at which corrotation with the star would require motion at the speed of light. Beyond the light cylinder, the field opens up and particles stream outward. In a magnetar, the field is not only stronger, it is more dynamic. The magnetic field, threading both the core and the crust, can be wound and twisted by differential rotation between the core and the crust. As the internal field evolves, it exerts torques on the crust. The crust resists until it cannot, and then it fractures. The fracture sends a seismic wave through the star. The maximum shear wave speed in the neutron star crust is approximately 1% of the speed of light, 3,000 kilometers per second. A seismic wave propagates around the 20-kilometer circumference of the neutron star and returns to its origin in approximately 60 microseconds. This means that seismic oscillations of the neutron star, quasi-periodic oscillations, or QPOs, have characteristic frequencies in the range of tens to thousands of hertz, and those oscillations have been detected in the X-ray light curves of magnetar giant flares. After the 2004 giant flare of SGR 1806-20, and after a 1998 giant flare from SGR 1900+14, detailed analysis of the X-ray data revealed oscillations in the brightness of the decaying tail of the flare, repeating modulations in the emission at frequencies between approximately 18 and 1800 Hz, persisting for hundreds of seconds after the initial burst. These oscillations are believed to be the seismic ringing of the neutron star itself, the stellar equivalent of the way a bell rings after it is struck, with characteristic overtones set by the geometry and composition of the object. These quasi-periodic oscillations provide a direct probe of the interior of the neutron star. The frequencies at which the crust rings depend on the shear modulus of the crust, how stiffly it resists deformation, and on the coupling between the crust and the superfluid interior. Different equations of state predict different oscillation frequencies. Comparing the observed frequencies to theoretical predictions is one way to constrain what the interior is made of without being able to look inside. It is, in a sense, the same method a physician uses when tapping on the body to assess the condition of an organ. The crust of a neutron star rings. The frequency of its ringing tells us something about its structure. The instruments listening to the ringing are X-ray telescopes in Earth orbit, sensitive to photons arriving from an object 30,000 light-years away. The star told us its secrets in the only way it could, by shaking. The star turns approximately once every 3.25 seconds. This is a rotation rate far below the death line for ordinary radio pulsars, which is why SGR 1935 plus 2154 does not normally produce a standard coherent radio pulse with every rotation. What it produces instead is sporadic, intense, associated with its surface activity rather than with the steady sweep of a beam. Magnetars are young. The ones we observe are typically less than 10,000 years old. Their fields are so strong that they decay rapidly on astrophysical timescales. The energy stored in the magnetic field bleeds away through the processes of ohmic dissipation and ambipolar diffusion. The timescale for significant field decay in a magnetar is estimated at roughly 10,000 to 100,000 years. After that, the field has decayed to the level of an ordinary young pulsar, and the object is no longer a magnetar. This means that the magnetar you are near is passing through a brief phase in the neutron star life cycle, a few thousand years out of a potential billion-year history. It was born with this extraordinary field. It will not remain extraordinary. It will age into something quieter. The violence is temporary. The universe cannot sustain these extremes indefinitely. Energy drains, fields decay, rotation slows, things quiet down. Everything quiets down eventually. The most violent objects in the galaxy are only violent for a little while. Now let us bring everything together. You have traveled through 5 different contexts tonight. A young pulsar in its first thousands of years, the interior of a neutron star, down to the edge of the describable, a kilonova, the merger of 2 neutron stars, the forge of the heaviest elements, a millisecond pulsar, old, recycled, serving as a gravitational wave detector in a network that spans the galaxy, and a magnetar, the most magnetically extreme object known to science, connecting to the fast radio bursts that illuminate the intergalactic medium across the observable universe. All of these are the same class of object, a sphere of neutrons and exotic matter, 20 to 25 kilometers across, with a mass between roughly 1.1 and 2.3 times that of our Sun, born in the catastrophic death of a massive star. The differences between them, the pulse rate, the field strength, the age, the presence or absence of a companion, the degree of accretion, produce the full range of phenomena we have visited tonight. One object type, an entire landscape of astrophysics. The universe does not need a different mechanism for each phenomenon. It needs one object in different configurations at different ages with different histories, and the range of behaviors follows inevitably from the physics. The laws do not change. Gravity, the strong nuclear force, electromagnetism, the quantum mechanical behavior of matter at extreme densities. These are the same in every neutron star in every galaxy. The diversity emerges not from new laws, but from the application of unchanged laws to varied circumstances. And those laws have been tested with neutron stars in ways that would not have been possible with any other kind of object. General relativity, Einstein's description of gravity as the curvature of space-time by mass and energy, has been tested with neutron stars more precisely than almost anywhere else in the universe. The timing of binary pulsars over decades of observation matches the predictions of general relativity to better than 1 part in 100,000. The rate of orbital decay due to gravitational wave emission, the advance of periastron, the slow rotation of the elliptical orbit's orientation in space, the Shapiro delay, in which pulses arriving from behind the companion are measurably delayed by the curvature of spacetime near the companion's mass. All of these have been measured in binary pulsar systems, and all are consistent with general relativity to precision levels that exceed many laboratory tests. The double pulsar, PSR J0737339A/B, discovered in 2003 by a team led by Marta Berge, is the only known system where both neutron stars are active radio pulsars. One spins 22 times per second, the other spins once every 2.77 seconds. They orbit each other in just 2.4 hours at a separation of less than a solar radius. This system is the most relativistic binary known in the galaxy. 14 distinct tests of general relativity have been performed using this system, using phenomena including Shapiro delay, gravitational redshift, and geodetic precession, the slow wobble of the spin axis of each pulsar due to the curvature of spacetime in the other's gravitational field. All 14 tests are consistent with Einstein's theory. Two dead stars, spinning in their orbits around each other at a separation smaller than the Sun, have tested and confirmed our best theory of gravity more precisely than any other system we know. The observations of neutron star masses and radii, from X-ray timing, from gravitational wave analysis, from nicer surface mapping, provide constraints on the equation of state of dense nuclear matter. The combined analysis of GW 170817, nicer observations of PSR J0030 plus 0451, and PSR J0740 plus 6620, and the catalog of known neutron star masses from pulsar timing has, over the past several years, narrowed the range of viable equations of state significantly. Dense nuclear matter is neither extremely stiff nor extremely soft. The radius of a typical 1.4 solar mass neutron star is most likely between 11 and 13 kilometers. The maximum mass is likely between 2.2 and 2.5 solar masses. Each new observation narrows the range. Each narrowing is a step toward understanding what the universe does with matter at the most extreme densities accessible in its current epoch. These are not abstract questions. The strong nuclear force governs every nucleus in your body. The precise way in which protons and neutrons bind together, the binding energies that determine which nuclei are stable and which decay, is set by the same force whose behavior at high density we are trying to understand through neutron star observations. The neutron stars are telling us something about the force that holds your atoms together. The physics of your body and the physics of the most extreme objects in the universe are written in the same language. It is a long sentence, but it only has one grammar. You carry those same laws inside you. The carbon in your cells was made in a stellar interior. The iron in your hemoglobin was made in a supernova. The gold in any jewelry you own, or in the electronics in your home, was made in a kilonova, in an event like the one you witnessed tonight. The calcium in your bones was synthesized in stellar cores over billions of years and distributed through supernova explosions into the interstellar medium, gathered into the solar nebula that formed the Earth, dissolved into the oceans, incorporated into the shells of marine organisms, compressed into limestone, weathered, dissolved again, and eventually incorporated into your skeleton. You are the product of the same physics that produces neutron stars, not metaphorically, literally. The forces that govern the behavior of matter inside a neutron star, the strong nuclear force, electromagnetism, gravity, are the same forces governing the atoms in your body right now. The neutron star is an extreme environment in which those forces operate under conditions we cannot reproduce in a laboratory. Your body is a moderate temperature, moderate pressure, complex biochemical environment in which those same forces operate with extraordinary subtlety and precision. The neutron star and the sleeping body are not opposites. They are different expressions of the same underlying physics. You are made of the same laws as the most extreme objects in the universe. Those laws are holding you right now, as gently as they hold everything. Let that be the last scientific thought of tonight. Not a fact about a specific pulsar, not a measurement, not a distance, or a field strength, or a rotation rate. Just the knowledge that the physics you are made of is the same physics operating at the far ends of possibility, in the crushed interiors of dead stars, in the collision clouds of kilonovae, in the precise tick of millisecond pulsars, in the explosive magnetospheres of magnetars. There is no division between the physics of the universe and the physics of you. There is only physics expressing itself at different scales, under different conditions, with different outcomes. You are one of those outcomes. The one that can lie still in the dark and know that the stars are out there. The one that can hold the size of the universe and feel not diminished by it, but continuous with it. The night is quiet now. Your room is the same room it was when this began. The dark is the same dark. Your body is the same body, breathing, warm, held by the gravity of a planet orbiting a star that will one day, in approximately 5 billion years, expand, shed its outer layers, and leave behind a white dwarf, not a neutron star. The sun is not massive enough for that, but its core will remain dense and cooling for longer than the current age of the universe. Even the ordinary stars leave something behind. You are lying inside the remnant of a star that exploded billions of years before the sun was born. Every atom in your body passed through at least one stellar interior before the solar system existed. You are, in a very precise and literal sense, stardust, a word that has become so familiar it has nearly lost its meaning, but which is simply true. It is a small thought to fall asleep with, and also the largest one available. Let it settle the way objects settle in low gravity, slowly, without impact, touching down so gently that the arrival is barely distinguishable from the approach. Your breath is slower now. It has been slowing throughout this night, gradually, in the way that pacing a narration slowly tends to slow the breath that listens to it. The room is still. The stars outside, even if you cannot see them through a ceiling or clouds or the light of a city, are still there. There are 2,000 known pulsars in the galaxy. There are estimated to be 100 million neutron stars in the Milky Way alone. There are hundreds of billions of galaxies in the observable universe, and in each of those galaxies, there are neutron stars, spinning, radiating, merging, recycling, building elements, detecting gravitational waves from the collisions of supermassive black holes, and occasionally flashing across intergalactic space in bursts of radioluminosity bright enough to be detected a billion light-years away. All of this is happening right now, not in a story, not in a model, in the physical universe, in the space outside the atmosphere above your head, in the galaxy whose disk you are embedded in. It is happening while you sleep. You do not need to attend to it. It does not need your attention. The pulsars will pulse whether you are awake or not. The kilonovae will occur in distant galaxies, regardless of whether anyone on Earth is watching. The millisecond pulsars will accumulate timing residuals in the nanograv dataset. The magnetars will stress and fracture and occasionally flare. The physics will continue as it has continued for 13.8 billion years, patient and precise and entirely indifferent to whether any mind is present to observe it. The universe does not require your vigilance. Everything will still be here in the morning. The pulsar at the beginning of tonight's journey is still turning, 23 times per second exactly. The radio beam is sweeping outward through the nebula. The X-rays are flowing from the surface. The superfluid interior is threading its vortices through the rotating crust. The neutron star does not know you were near it tonight. It does not know anything. It simply continues, in perfect accordance with the laws that govern it, for as long as those laws apply. And 350 light-years from your home, PSR J0030 plus 0451 is turning 205 times each second. Its hotspots are glowing. Its X-ray photons are falling, one by one, onto the NICER detector in Earth orbit. Its pulse is arriving at radio telescopes in New Mexico, in West Virginia, in Parkus and Effelsberg, and Beijing, being time-stamped to nanosecond precision and entered into timing residual files that will be analyzed years from now, contributing one more epoch of data to the gravitational wave background detection. Let it happen without you. It knows what it is doing. Your breath in. Hold for a moment, soft and natural, the way a pond is still between ripples. And out. The night is long. There is no reason to rush anything. Not sleep, not thought, not the gradual quieting of whatever is still moving in your mind. Things quiet on their own schedule. The pulsar did not quiet on demand. It took millions of years of energy loss to slow from its birth rotation. Your mind will take the time it takes. That is not failure. That is the normal behavior of a system that processes information, which is what a mind is. Let the processing continue at whatever pace it continues, and let your body rest regardless. In. Out. The universe is 440,000 times older than the oldest known pulsar. It has been running its physics experiment for 13.8 billion years, producing stars and exploding them and building elements and distributing them and forming new generations of stars from the remnants of old ones, and occasionally, in the process, producing objects like the ones you visited tonight. Neutron stars are not accidents. They are expected outcomes, products of a chain of physical events that follows inevitably from the initial conditions of the universe and the laws that govern it. So were you. Not this specific configuration of atoms and memories and sleeping mind that is contingent in ways that are genuinely complex to trace, but the general outcome of the universe producing self-aware beings who can lie in the dark and understand something about neutron stars. That outcome was always available to the physics. It required certain preconditions: planetary systems, liquid water, carbon-based chemistry, evolutionary selection, long enough timescales. All of those preconditions were met in the same galaxy where the pulsars are turning, on the same pale blue point that orbits an ordinary star in the outer third of a spiral arm of the Milky Way. The universe made the pulsars and the mind that can know about them in the same place, in the same galaxy, from the same raw material. This is not a reason for pride or for smallness. It is simply a fact, a remarkable one, but a fact. You are the universe's capacity to know about neutron stars, resting in the dark, letting the knowledge settle, allowing sleep to come. The pulsars are out there. They will still be turning in the morning. You can set this down now. Set it down. Let the breath come. Let the dark hold you. Let the ordinary miracle of sleep do what sleep does: the consolidation, the restoration, the quiet biochemistry of a body maintaining itself through the night. You do not need to remember the reprocess or the dispersion measure or the Hellingsdowns correlation or the crescent-shaped hotspot on PSR J0030 plus 0451. You do not need to hold any of it. It is in you now. The way things absorbed in a calm state tend to sit quietly in the deeper layers of memory, present but not demanding, available but not intrusive. Like a pulsar that is no longer pointed in your direction, still turning, just not visible from where you are tonight. If tonight helped you rest, if the science gave your mind something real and calm to settle around, please subscribe to Quiet Science at Bedtime, leave a like, and turn on notifications so you know when the next journey is ready. Thank you for being here tonight. Good night. The pulsars are turning. Sleep well.